I just want to give a brief introduction to our webinar speaker this afternoon. So Tom Les, he is a bridge engineer and a senior associate at, and also a team leader at Woolpert in Ohio. He's the president of the American Society of Highway Engineers in Central Ohio section. His expertise is that he's highly skilled in analysis and design of bridges, including complex geometry, historic, rehabilitation, pedestrian suspension bridges, and non-standard materials. So yeah, that's Tom Les. Tom Les is a MIDAS expert user in our MIDAS expert network, and we'll give you a brief introduction of the MIDAS expert network right after Tom's presentation and Q&A session. And I think, Tom, you can start. Go ahead.
Okay, I'm going to turn on both webcam here and sound. If I get choppy at all or anything, please do let me know, and I'll turn off the webcam in case it's a bandwidth issue, but I can at least start that way. So thank you and welcome everyone to the webinar. Thanks to MIDAS for inviting me to present. I'm going to be covering load rating, as described of complex geometry structures with focus on composite steel. Although a lot of the concepts here can be carried into pre-stressed or post-tensioned or whatever else you're looking at. So with that, we'll get started here. A quick outline of what we'll be going over. I'll just give a quick personal introduction, although I think it's already been covered, but just a little bit about myself. Load rating overview. And I'm trying to not go too in-depth there. I assume that we've kind of got a wide array of experience here on this webinar. So some of you may have, maybe never done a load rating before. Some of you may be pretty familiar with it, and some of you may be experts in it. So hopefully I'll try not to keep it too boring for those of you who've got a lot of familiarity, but just to go over some of the general concepts to make it accessible for everyone. Some structure types recommended for advanced analysis and what types of advanced analysis we might be looking at, because there are different types. And then some MIDAS modeling pointers discussion, a couple example projects, generally how you do it in MIDAS, actually stepping through those menus, and then reporting or equivalent live load distribution factors, how you get this into nice report formats as far as your end result. And then we can take any questions. And I know there's another session after this that's more pointed for some specific people who pre-signed up for that. So that's what we'll be covering here. Again, I'm not going to go through all this, but as JC mentioned, I've got a lot of experience in curved structures, flared framing plans, complex spiral to tangents, suspension bridges, advanced modeling in general. Licensed as PE and SE, also experienced with some high seismic design regions. And then I've been a MIDAS civil expert, I think for 2 years now, something like that, in their program. I also do a lot of work with Engineers Without Borders, so just going to do a shameless plug there. This is a project in Guatemala that worked on in high seismic zone 4. So again, kind of goes with the analysis side of things, a little bit more complex, a little more difficult. If you don't know Engineers Without Borders, check them out. Shameless plug. For my firm is Woolpert. We've got about 900, actually close to 1,000 now, employees, founded in Dayton in 1911, and about 30 offices worldwide now as well. And most of that's in the US with a little bit of Canada and now South Africa. We do a large number of different types of things. I'm not going to spend a lot of time on this, but you can see some of the areas that we cover. My focus obviously is a little more in transportation, a little bit in Parks and Rec, and a little bit in aviation. So load rating overviews. There's some nice documents out there. If you've done any type of load rating, you should be familiar with Manual for Bridge Valuation, AASHTO LRFD, and LRFR are pretty stock standard stuff. There's some additional, documents in here though that I wanted to point out. There's a load rating of steel bridges handbook. I believe that is a little out of date now, but all the concepts are pretty much the same. So that has not changed, what you're really trying to do. Maybe a couple factors here or there, but if you see archived on it, don't worry too much about that. Yeah, you need to look at the current code, but in general, the concepts are not different. There's also an FHW manual for refined analysis and bridge design and evaluation. which is pretty useful in getting deep into some of the concepts around finite element analysis, best practices, that type of thing. FHWA's got a load rating resource page, and then this FHWA NSBA partnership guidelines for steel girder bridge analysis is a pretty detailed and extensive kind of dissertation on the topic of all the different kinds of ways you can model these types of structures. So just trying to give some resources there that will go into much greater depth than what I'll be able to do in an hour, and to give you, something that you can look at after this as well. So some general definitions here, just to make sure we're all on the same page. Really, load rating is the live load carrying capacity. So you've got your capacity, subtract out all of your dead load, superimposed dead load, moments and shears, and then what's left for the live load, and you can get to a rating factor, essentially. Usually expressed as a tonnage, or just that single rating factor number, which is a multiplier of the vehicle. So 1.0 of HS20 would be, can take just an HS20. Generally, load rating is that ability to carry the live load for design and allowable legal vehicles, overloads, determine weight postings. There are some differences when we're looking at a load rating from what we do in bridge design. Not a huge difference here, but you're mostly just, again, capacity to demand and comparing the two. But it's a little bit different treatment of some of these. There's a more conservative reliability index in design. And what I mean by that is that you're usually looking at like 1.75 for your live load factor, whereas you get into operating rating factors and you're lower on your rating factor. And part of that is that you look at it from as far as the reliability index and how that's generated. You're really looking at how well do you understand or know what the loads are going to be and what your material is going to be. So as you have a better grasp on exactly what that loading looks like, then you can reduce your live load factor associated with that. And that's really why when you look at legal vehicles, or in particular the overload specific posting vehicles, if they're running a very specific overload that exactly the axle configuration and your weight to a pretty high degree of accuracy, then that live load factor could come down a bit from the 1.75 to more of the 1.3, 1.35 range, which is what code allows you to do, because that's more well known. And that kind of plays into how, again, that reliability index is generated within code. So that's a little bit of a longer discussion about that, kind of the background of why that is the case. But again, as you know what you have more thoroughly, you can reduce factors. As you don't know, with like standard HL93, that carries the 1.75 at the inventory because you're trying to capture those unknowns. This bridge design can also account for environmental loads, wind, seismic, all that kind of stuff that load rating typically doesn't. The main thing is it's a probabilistic problem where, just from a are you really going to have the worst case loading you've ever had on the structure at the same exact time as you get a, extreme event earthquake? Very unlikely to happen. So we don't usually design for that or load rate for that because it is such a low probability event that those might happen at the same time. So again, a little lower on the environmental loads, really focusing on the live load, dead load, DW, depending on what your state's guidance is, or general governing authority, I should say, maybe your province or wherever else. So again, load rating types here, we got inventory and operating, those carry the different factors as discussed. We're going to look at a single safe load capacity per configuration for the legal loads. Again, those are at operating level typically. Some states can modify that. They may ask you to do it at inventory level as well. Just going by the general FHWA model for the United States, that's typically how. And then the permit load rating would be applied to specific overloads or permit loads, usually by your state DOT, Department of Bridge Management, or whatever their equivalent is. The general rating equation is as shown above here. Basically, just as I quickly described, capacity minus your dead load factor times the dead load component minus the DW or future wearing surface times the DW component, And then if there's any additional permanent load from whatever else there might be, permanent settlements or anything else that's really just permanent on the structure, then you're dividing that by your gamma L, which is your live load. That's the 1.75 or 1.35, and then live load plus impact. So that really gives you that overall rating factor. Again, the capacity minus everything else divided by the live load, and then whatever version of that. If it's 0.75, that means you can't carry that full truck. If it's 1.5, you can do 1.5 times that truck at that configuration. And there's conditions states here too. So if you have condition factors, you'd incorporate those as well based on if it's a load rating of an existing structure that might have deterioration. In the United States, FHWA generally controls this. You've got the 2F1, 3F1, 4F1, 5C1, these different configurations with different axle setups. The SU series, SU4, 5, 6, 7. Again, just different axle configurations. I won't spend a lot of time on that. The FAST Act, which was signed into law in 2015, added the EV2 and EV3 vehicles. These are emergency vehicles meant to model mainly the really heavy ambulances or potentially a fire truck or some type of fire vehicle. They're quite heavy. They did cause a number of issues for states. Depending on your state laws, how this got implemented could be different. So if all vehicles are allowed on all routes as far as emergency goes, then you might have been required to redo load ratings and everything to incorporate these EV2 and EV3s. I believe the deadline is probably, I think it's still 2022 or might be 2023 to reload rate in those situations based on whatever your FHWA to state DOT agreements might have. But I do think there's a deadline coming up the next year or two to make sure that those are all incorporated. Now, if your state does not allow them kind of anywhere and restricts their usage in terms of where they can be driven, that's another different case where you might be only load rating a subset of your state inventory. So it's very much a state-to-state thing, depending on how the law is written within your state, how the DOT is handling it, and how FHWA has agreed. Now, FHWA did allow you to use a lower factor of 1.3 here instead of the 1.35. Again, recognizing that these are a little bit better understood as a weight and axle configuration. The other thing that has been done sometimes is identifying where the hospitals are that have these vehicles, and then only rating the stuff within that region, within that county or jurisdiction, in order to kind of restrict how much we're really implementing this. So that's a little bit on the types of vehicles, and there's going to be other vehicles out there. Every state may have additional legal loads. I know certainly like Michigan's got a large number, but you know, each state's different. Look at your state guidance, and you can add those appropriately. So I'll get into structure types recommended for advanced analysis. So why do we do advanced analysis? Why not just do Girder line? Curved is certainly a big component to that. You've got a lateral moment and lateral capacities and loads that you've got to deal with. Refer to the AASHTO 4612. It gives you a pretty good description of when this is warranted. So, you know, you usually hit a certain point where cross frames are primary members. That's a little bit different than treating them as secondary members. You know, when it can be ignored here. So you've got to meet these things in order to ignore the curvature. Concentric beam lines, bearing lines not more than 10 degrees from radial. Everything's pretty similar on stiffness. And then your arc length over girder radius is less than 0.06 radians. So basically low curvature, pretty, you know, standard bridge, very similar stiffnesses. Then you may not need to do this. But you start getting beyond any of those things. Things aren't concentric. You've got multi-skew, or you've got a skew that's off from radial. You get into tighter curvature. That's where code is going to tell you you really need to kick into a more advanced analysis. Highly skewed structures, so greater than 30 degrees, the lateral stiffness of your cross frames really starts to kick up and cause redistribution of moments and shears. So, you know, when we start getting into higher skews, you know, that's another trigger that makes you need to kind of move over towards this. Unusual framing, so flared, or you've got header beams, beams that end, at some type of terminator, and usually that's more on a flared structure that's kind of coming in from a wide structure to a narrow structure. Dog-legged, which is another treatment. Instead of doing a curved beam, coincident with your curved deck, you might do, particularly older structures oftentimes do this. They'd have a dog leg where it kinks throughout the system. And then, sometimes you need to load rate things like piers and substructure elements, particularly fracture critical piers, steel piers. You refer to the MBE, it'll tell you when those are warranted. But that can be something that you may have to get into as well. It's not just load rating superstructure, but the substructure as well. There's a nice guidance in this out of this guidelines for steel girder bridge analysis, which I had the link earlier in the presentation. And they give this nice chart. So what they're showing here on the right side of the screen is essentially different analysis methods and how well they compared to a full 3D analysis. So you've got different criteria there as far as the response goes: major axis bending, vertical displacements, cross-frame forces, lateral bending stresses, which is really the curvature component to things, layover at the bearings. So you've got all of these different parameters, and then kind of some general ranges of stiffness that you're looking at for comparison. And again, these are dealt with pretty in detail within the that manual, and you can go read that. I also did for MIDAS a similar presentation to this back in 2018, I believe it was March 2018, comparing some of these methods within MIDAS as well. So you can go back, I believe, online to MIDAS and find that presentation if you'd like to. So I won't spend a lot of time on it today. But just to note, and traditional 2D grid, oftentimes called grillage, is that first one there. The 1D line girder, obviously your standard old school method of doing things, maybe modified by VLOAD or MR methodologies. And then the improved 2D grid, I sometimes call grillage plus. Sometimes, it's 2.5D. I've seen different terminology for that one, which is really the one that you most often are doing in MIDAS, is the improved 2D grid, which is, you're doing an eccentric beam from your deck, and then you're fully implementing the 3D cross-frame stiffness. So even though the beam might be a single element, and it's really more of a grillage at its core as far as the beam goes, you're incorporating the full stiffness of the cross frames. And that's the real thing that makes the 2D improved grid, 2.5D, grillage plus, whatever you want to call it, different from that traditional 2D grid. And you can see the scores there. That improved 2D grid, basically A, B's, a couple C's there as far as how it compares to the full 3D analysis. It's pretty good correspondence there versus you're seeing, the traditional grillage or the 1D where you're getting into D's and F's on some of these where they really just can't capture some of that structural response. So some discussion, I kind of already went over this, but the traditional girder line with VLOAD, which you often use for preliminary design on these type of structures. Then you get into that 2D dimensional grillage analysis and grillage 2D plus, again, like I just described, and then full 3D. Main differences here: girder line modeling, is going to use standard live load distribution factor. It can be done minimal time, not complicated. You can add VLOAD into it using spreadsheet forms or other methods. To try to incorporate some of these two-dimensional or three-dimensional effects, at least approximating them. And generally, it works pretty well for, again, preliminary. Now, when we're doing load rating, we really kind of want to get deeper into it than that. But it may be an option if you get into that situation where maybe a 1D is all that's warranted by code, but you want to incorporate some of these effects. Maybe VLOAD's a way to do that for you. And the theory here is basically, you're trying to capture, that lateral moment as force couples. You can kind of see there on that right figure. And you're essentially taking that girder and just straightening it from its curvature to a straight girder of equivalent length along the arc. You really kind of need to have pretty large radii. maybe 1,000-foot or larger radii on it to make that more accurate. And then there's a number of limitations there again on the 46224 on deflections, reactions, twists, that kind of thing. Grillage analysis, that's like I described, you got beam elements offset with plates, you're capturing your lateral stiffness. And, went over all that, and then the 3D analysis, which is the full amount. Now in MIDAS, you're going to see this as the deck is plate, beam is frame. That's going to be your 2D plus for what you select there. And again, that's those plate elements offset with the beam. The all frame is going to be your full 3D. It does increase run times. It also, the all frame is not as automated in terms of being able to extract rating factors directly out of that. MIDAS is really set up more for the deck as plate, beam as frame when you get to the back end of it, trying to extract that stuff out. So that's the one I would most often recommend unless you have something very unusual. And here's kind of what that looks like. A tip that came out, and I sent this into the MIDAS folks who forwarded this on, I saw in an email. I often will renumber all of my nodes, and this really does help with a lot of your extraction and back end, is to, essentially select girder line 1 and start it at 10,000 to whatever. Girder line 2 is 20,000 to whatever. Cross frames, you can do the same thing so that all the cross frames are numbered together. That makes it really easy to pull stuff out of it, because you can just say, I want to active all only girder line 10,000 to 10,900, and it just grabs only girder line 1. Or, when you're doing your reporting tools, you don't have to go look for any of those elements or nodes, because you'll know already which ones you're going to try to pull out if you want to do a specific girder line or a specific set of cross frames. It definitely makes the output a whole lot easier and a whole lot faster to manipulate. So just a tip for everybody if you don't already do that. The modeling, again, 3-dimensional, gives you the accurate distribution of live loads. That's one of the biggest differences here between any of our 2D or 3D methods and the girder line is the live load distribution factors, that we're actually doing an influence surface instead of an influence line. And because of that, we can position trucks at different spots in order to create. Again, the lateral stiffness and distribution of the forces is also captured. The internal forces are captured in the 3D that aren't quite captured in the 2D plus. And then you could also account for things like tension field action in that full 3-dimensional, but you do have a little bit of a drawback here that the reporting side, when you're looking at code, is all based on a lot of like moment calculations or shear, whereas in a 3-dimensional model, you're really dealing with stresses. So because of that, some of the code checks don't really work in the 3-dimensional, or at least not easily. You can get it out, it's just much more difficult. And I won't go into post buckling and tension field here. Just know that they're there. Do it 3D if you're really looking into it. And you find that in MIDAS here during your composite girder wizard. You've got the all frame, all plate. The deck is plate, girder is frame, which again is the most common that I think is generally used. And then there's a deck and web as plate, flanges as frame as well. Here's an example of one that we did. This is a curved structure at the Cincinnati airport, highly curved. The radius of the center line is 200 feet, so it's a very tight radius to it. The minimum girder radius was 181. You can see it covered almost a 90-degree subtended arc, and it had 8 spans ranging from 48.5 to 68 feet. Everything was radial though, so that is nice. It's radial, no unusual skews, but highly curved. And we did do construction stage, as I'm kind of showing here. One of the main reasons I really like MIDAS is the construction stage abilities. And as a note here too for construction stage, but also as we get into some of the discussions around how do we implement the lateral bending forces and stresses, is around this provision here, which is in design of flanges where there's lateral bending stress that exceeds 0.6 FY, that you have to check that a little bit heavier. Code's a little unclear. This is really more for constructability cases, but it also can apply to service and strength depending on how you're looking at it, which is in that 610.16. And again, that normal check equation FBU, I should explain that, I guess. FBU is your primary main moment or longitudinal moment stress plus 1/3 of FL being your lateral stress in a flange. So you combine those two together as a combined stress check, and then we're going to look at that, and really you're mostly defined by that major axis bending, that FBU. And they've got this limit of 0.6 FY that is sometimes incorporated. They have it as a recommendation. And this is really trying to make sure that we're limiting our stresses and making sure that the assumptions in code, that is to say that our major axis bending controls the behavior of the beam, is accurate. So you do want to check that and make sure that your FL is not getting outside of these bounds, outside of that 30 KSI out of the 50 or 70 that you might be using. They kind of just say somewhat larger is acceptable. It's an engineering judgment thing based on just what you think is acceptable as far as that goes. So if you're in an area where there might be really low composite action, you may just have to treat the beam a little different or do a couple extra checks, more looking at lateral moments. Generally in the case of this structure, we allowed up to maybe 10 to 20% over 0.6 FY. A lot of that was due to the fact that we were pretty short on our girders, and the overall checks were below, as well as not really having layover issues. So again, you might have to use some engineering judgment with that one. Code's not really super clear. As you get into that too, really looking at your boundary conditions is very important. What are your bearings doing? So this was a new bridge, so we were able to control that a lot more. And what we did was we basically took our girder line 3 and we used that as our restraint line. So at this point right here, girder line 3 at the central pier, that's a true fixity for thermal. And then from there, we basically controlled the lateral perpendicular to the center line here of the girder along girder line 3 as the control line. Everything else floated on the bearings. Now, if you get into an existing structure that you're load rating that's already there, you really need to pay attention to what are the bearing settings. How restricted are those? Are they fully engaged to their maximum extent, and that they're actually going to provide more of a fixed or restrained condition in a certain direction, one or the other, transverse, longitudinal, however you're looking at it. That's really important when you get into analyzing the structure to make sure that those boundary conditions are correct. I did do this, and I didn't pull this one up, but I did a failure analysis on the Jennings-Randolph Bridge, which is, there's approach structures, multiple curved structures coming into one, and then they go across one of the largest Pratt trusses in North America over the Ohio River. But they had failures, bearing failures occurring and starting to propagate into the beams. And the big thing was that the bearings had locked up. They were pot bearings that had exceeded their maximum rotational extent. Plate touched plate, didn't have anywhere to go, and starts putting force into the girder, into your system. So you want to make sure that things are free to move. If they're not free to move, we need to identify that and incorporate it into the modeling. In this case, we had retainers, which we did a separate analysis on. Again, this was more from the design side, but you could look at it if you needed to. Really, from a load rating, you're only going to look at primary elements. You're not going to look at secondary elements. I just mentioned it here of the fact that, again, you can put a lot of force into some of these other components, and you want to know about that. And that's the completed structure there. You can see the upper level swings around on a pretty tight radius. There's a lower level that's swept under as well. This is another project that we used MIDAS for and did the load rating in MIDAS. one of the nice things, if you do the design in MIDAS, then everything's set up to do the load rating. So, once I've built it once, I don't have to go build another model. I just go to the next tab and do the rating. This one is a little different. It's skewed and curved. We got a 60-foot span, 286.9, and then a 60-foot or 61-foot, 19.5 degrees skewed to the reference chord, which also made it out of skew or skewed to the radial line. About 1,200-foot radius, a much bigger radius on this one, and a much lower curvature amount. But there was a vertical sag as well as a horizontal curve, so we have both of those happening. And then we also had part width construction, and that part width construction included temporary supports under pier caps during a live load situation. So we're actually looking at load rating of the temporary condition where we've cut the bridge in half, and we've got temporary supports under the pier caps. So we got to load rate those. So here's the framing plan on that. You can see that there's a skewed substructure and then a curvature to the structure. Things tend to be all radial as far as the girder lines go, but then just the supports, the splice locations, everything is to the skew. And you can see kind of what that looks like. This is before we did our new structure. So this is the existing condition before we came in and replaced it. But you can see the curvature of that existing. The existing was on dog-legged, and then we went to rolled and radial. Here you can see the MIDAS model of the phase construction. So that's where we've cut it in half. This pier was only then on one column, which makes it non-redundant. So that's an issue. So we built into it the temporary support towers, which were steel frame towers. And those sat on a common footing, and that footing sat on piles. We didn't really see the need to take it down to the piling level. So we just built it to the footing and did fixity or pin connection as appropriate for those elements. One of the big things here that's useful in MIDAS is that you can do your checks on not just the composite girder, but also on the reinforced concrete section, standalone, and on the steel standalone section, all within the single model. So you're not going to different modeling softwares or taking that out into other sources, spreadsheets, calculations. It can all be done within the one model. And that load rating is the same way. So that's very useful and very nice. The other thing here that's important is we're also capturing the relative stiffnesses of things. So that pier cap is much stiffer than this substructure. And what we found was we ended up having to increase the size of some of these members, not for strength, but for stiffness, because we want this steel tower to suck up the load. And what we're seeing happening is as you put a truck out here on the edge, that because this pier cap was much more rigid, it was pulling more of the moment into the pier cap than it was putting into this, because it's all deflection based there. That you've got a situation where there's a bearing under that, and you need full engagement of that tower. And as that deflects, again, you need to make sure everything's corresponding between the deflection as a cantilever beam of your pier cap and the vertical displacement, basically squishing that tower of axial compression forces. So those have to all work together. Again, within the MIDAS model, we're able to do that and do everything in one to capture all of these stiffness effects. And that's also the same is true for load rating as well as design. Here you can see kind of what that looks like. Steel frame tower with a header beam underneath that, and then bearing jacks to connect the two. We have some restrictions in the plans for full engagement of bearing jacks and all of that. Here's a third example of one that we've done. This was a Tuscarora 77 that actually had a flared framing plan, flared deck width, and you can see on the left side here, rear abutment, everything's pretty much standard and a little straighter, and then these two girder lines start to tweak in as you go across this. This was an existing structure, and the other thing that was of note was the substructures were not built as per plan. They actually ended up being a multi-skew. And even though it's only a couple degrees different, the fact that every one of these substructures was a different skew and substantially enough that we had to incorporate in modeling did add to the complexity of what we're trying to do here. So we had multi-skew with a flared framing plan that really kind of kicked us over into wanting to put this into more of that 2D plus finite element analysis to get the proper lab load distributions. So in MIDAS, I'm going to go through this a little bit here in presentation form, and then I can kick back into actual MIDAS software itself to kind of show where these menus are. So to start that, basically you're in the rating tab. You'll go to this bridge load rating design and steel design, and then you set your code. You're setting your parameters. Most of this is direct out of code. There's an update by code there, but say you need to use a different resistance factor, or you need to tweak things for either state requirements or because you've got a condition issue, you can tweak that all within that menu. Set what type of general parameters for your structure. Are you running this for service or just strength? All that kind of thing. You can directly enter unbraced length. This is important. And that's to calculate your lateral torsional buckling resistance and reduction in capacities. So if it's not inputted directly on the elements into MIDAS, then MIDAS is going to use your span information and just say it's the total span length if you've set up that span arrangement. If there's no span information, it's going to use the element length, which is much shorter than potentially the actual length between cross frames or supporting elements. So you really need to make sure that that unbraced length is set appropriately on all of your girder segments to make sure that the lateral torsional buckling is being incorporated appropriately. As far as the rating goes here, you can set your other parameters. If you want to look at fatigue, you can look at fatigue. A lot of times we're only looking mainly at the inventory and operating, not as worried as much about fatigue as far as load rating because they are unusual. Particularly your permit vehicles, you're not getting enough of those that usually fatigue is an issue, but you can also incorporate it if you so choose. You can put input girder radius into this. I will say, because this is going through the rating tab, this whole rating tab is really more on your capacity side of the equation. The analysis side is what's getting you stresses, moments, shear forces, all of that kind of thing. Then this menu system is really addressing the capacity calculations and what's being happening in the background as far as like the rating equations. So there's some parameters in code around if you hit certain radii that you need to incorporate different things. It's very similar to like hybrid Girder factor. So just be aware of it. You'll need to input it. It's not a big deal, but it's mainly just affecting that capacity side, not the actual analysis. Here's your rating materials. Again, you've got hybrid factors if you have them. What stress is your concrete, your concrete or your steel, and then reinforcement as well. You're inputting there. We set up our rating groups, and you can apply those condition factors, service limit, strength limit, fatigue limit, states, what primary vehicles, all your subset of vehicles, be they legal loads or those FHWA loads, the EV trucks, whatever they might be. You simply go down and add them as a primary vehicle and at what limit, state, strength, or service corresponding to the 1.75 and the 1.35 or inventory and operating. Really, they're all kind of the same thing here. So if you're looking at it from a strength limit, you're talking about inventory. If you're looking at the service limit, you're talking about operating. You can also put in all of your steel. So you got your positive flexure, negative flexure. You can see the standard equations that are associated with that. You can put in your steel reinforcement, transfer stiffeners, all of that. And then I'll get into a little bit here on the live load distribution factor discussion, and then I'll jump into actual MIDAS and then answer questions. So some states do ask for a note on the plans that indicates what the equivalent live load distribution factor is. And it's not a very easily determined number. It's not a single number either, because your influence surface is going to be different on a single girder line, whether you're at a negative moment region or positive moment region, or potentially if you've got a flared structure, where you are along the structure may have a continually changing effective live load distribution factor. States a lot of times want to look at this so that, if they wanted to take it into a very simplified girder line approach, that they could manually input that distribution factor and run a girder line to check things as a conservative number. So really, we want to be conservative when we're reporting these so that they could use it for that purpose. Now, again, it's not really quite true. The other thing is that distribution factor is dependent on your axle arrangement. So if you have an HL93, that's going to be different from, say, a 5C truck, because the axles are very different and the placement within your influence surface is also going to be quite different. So realistically, you have could have a continuing changing live load distribution factor along the whole length of the girder, and it's going to be different for every truck that you try to put on it. And a lot of what we're using MIDAS for is to incorporate all of these effects within our modeling system. But when you're trying to report it out as like single individual numbers, doesn't work so well. So if you do get a request for this, there's a couple ways to handle it. The way I've typically done this is just look at the maximum. Look at interior and exterior girders, or if you have flared, maybe it's the exterior, interior 1 through 6, and then you have like a 7, 8, 9 if there's different on those. And you're just trying to report that again for their overall goal of, if you tried to put this into like Merlin Dash or some other fairly simplistic girder line approach, what would you need to do that? So we're going to look at those negative moment, positive moment, and shear maximum live load distribution factors. And I typically only provide this as the HL93. I don't usually do this for all of the vehicles as far as my plan note goes. Again, HL93 is probably governing most of your design. Now, if you've got a different design vehicle governing it, you may want to do that for a different vehicle as well. But given that HL93 generally is what's driving most of our design, I usually report it that way. And again, we're handing off the model too, so they can just use the model as well, or ask us to rerun it if they have something specific. And again, that configuration discussion. So since MIDAS produces the maximum effect at each location, there's going to be variability. When running it, I usually just have a girder line comparison that I'm running anyway. Anytime you're doing finite element modeling, you should always have some type of backup verification calc. I mean, just general practice, you should be doing that. So I usually have a girder line that I've just straightened it and done V-load for like a curved structure, or maybe I've done, for a flared structure, I'll just do the worst case, beam spacing and just run that as a girder line for comparison. Make sure that it's in ballpark of what I'd expect. And if you do this, then you can do a pretty direct comparison between what's coming out of MIDAS as far as your maximum. So in this case, this would be maximum negative moment coming out of MIDAS over the girder line maximum moment, and then multiplying that by whatever your girder line live load distribution factor was, and that gets you a effective MIDAS live load distribution factor. It's pretty simplistic, but it's enough that it's something defensible. You want to look at this again as your maximum case, so that you're reporting the worst case distribution factor, and it's just a way to give that should they ask it. And here's a sample note of what that looks like. So in this case, I said the bridge is required the use of a grillage finite element, deck as shell or plate, and beam as beam or frame, which is that 2D plus. Design method to analyze the structure, computer program used for structural analysis by civil. Bridge components designed by this method are beams, splices, and cross frames. Basically, the superstructure was developed method. And then you can see here are distribution factors for exterior and interior, again at positive, negative, and shear. And these are just worst case, essentially. So that's a sample note of how you might incorporate that. Before we jump into questions, I'll jump out of the presentation here and go directly into MIDAS. So here you can see that highly curved structure that I had earlier. The design tab here, you've got all of your design sections, the composite analysis, composite design. And the rating tab is really what we'll focus on here today with the ratings. And I only ran a couple here, just right at the end, which is why you're Flexural rating is really high, obviously, because it's, you know, you're right at the end, low moments, not to be expected here. So your parameters here, you've got definitions of things. So member assignments, you can reverse directions, look at effective length factors. That's actually important for like that tower piece, or if you're looking at substructures, you might want to put effective length factors that are on axial members. Also for cross frames, if you're trying to rate a cross frame. Limiting slenderness stuff, unbraced lengths are all in there. The steel bridge here, this is basically what I showed. So you've got your code, rating code that you want to use. We have other parameters. This is all the stuff that was really out of the presentation, but just kind of popping through them to show where they are. Longitudinal reinforcement. So here's an example of one that's filled out. We've got our lower mat of steel, our upper mat of steel has been input. There's no shear reinforcement in that deck, obviously. You can define your rating cases. So here I've got a HL93 truck and tandem at the strength limit state applied. I've only loaded into this particular model set the fatigue, which is the HS20, the tandem, and then the HL93 truck. If you need to get to any of those or add additional loads, just go back to your load tab and you're going to go to vehicles, and then you can add user defined or add standard. So if I go to add standard, here you can see that I've got ASHTO, I've got different state loads that have been preloaded in, Caltrans, the different states, Ohio DOT, Missouri, Louisiana, Illinois. So those may be already in there. The EV loads that we were discussing, there's your EV2 and EV3. You just simply add them into your model. Now these do need to be added here on the analysis side of the house before you get to the design and rating side. So you can't just go add it directly into your rating menu. It has to be added as a load, and then you run your analysis, and then you can get it in your rating menu. So just there's an order of operations that you have to do there. When you go through this, again, it's pretty easy. You got transverse stiffeners, you can put those in size, 50 KSI and everything else that you're doing. Let's see. Unbraced length, as discussed. Curvature. Now, if you look at these, so say this curved bridge info, when I went to that menu, you can apply it to things. You can also look at tabulated forms. So if I hit this ... right here, it's going to pull up a separate window, and you can see that on this element, which again, my 60,000 series is my Girder line 6, these are all applied at the 218.75. Again, this is where if you numbered your elements like this, it makes it really easy to just select all the 60,000 to whatever and apply your 218.75. And then do the same thing for Girder line 5, which is your 50,000 series, and there's your 211.25. So applying a lot of these factors, it's not even just pulling it out, but applying some of the stuff on the design and rating end. If you do that renumber, it really makes your life a lot easier. That's also true for if you want to select, by beam here. So if I wanted to say that, I can just select those and then hit the active, and then now I just have that Girder line 5, and then you can active all. But again, it makes it very quick to select what you're trying to find. Let's see. Deck overhang loads, you can apply them in here for additional distributed force, concentrated loads, eccentricity of overhang loads. I tend to incorporate that on the modeling side as just loads within the modeling as opposed to within the separate rating. But there may be cases that you want to apply that as a separate load or a little bit differently outside of the design system, but actually within just the rating side of the house. And it seems like a pretty special case to me. I haven't really used it there, but it is available to you should you wish to use it. Let's see what else here. So position for rating output is just telling it where you want to do that. And in this case, I just did it on one element there to make it my life quick and easy. So that's on Girder line 2, the 10th element, at I and J being the first and the end node. So near node, far node, however you've got it assigned. and it's just going to output it for those locations. The rating design tables, you can have all that stuff pop out, and then perform rating design actually does it. Excel reports will export this to an Excel document, which is useful for your outputs of how states often like to look at those. So in this case, I exported one here, so you can see that my flexure rating at the HL93 truckload, capacities, demands, dead load demand, live load demand, rating factor is all displayed there. And in the load rating result table, you've got basically everything you need as far as putting this into a load rating report summary. So you've got your DC factors, DW factors, live load factors, the demand from the live load, what the critical element was if you're running out multiple, and then your rating factor. In this case, it was 1.18 on the truckload here and 1.34 on the tandem load, and this was at inventory level, and then your general live load, this was shear, demand and everything else. So that's basically how it outputs it for you. Now you might be wondering, how is the lateral stress incorporated in that? Really what you're looking at is there's a couple different ways to run this in MIDAS, and that is if we perform the rating result table here, you can see there's a strength limit state summary, a flexural strength limit, shear strength, and then a steel stress rating factor. And what you're really looking for, if you want to know that curvature effect, is you're going to use a steel stress, which is that FBU plus 1/3 FL compared to the overall maximum capacity stress based on lateral torsion buckling, any hybrid factors, whatever else you got. So that would fully incorporate the lateral moments that you're seeing. So the flexural strength one is really just looking at primary longitudinal. The stress is looking at the combined stresses. So and that would then output from there. So I think with that, we're about 3:54, which leaves us a couple minutes here, 5 minutes or so for questions. And then we can go into that separate session for those who had done the pre-sign up for a little more detailed discussion. So happy to take any now.
Right. So actually, before we get into the question session, we have a couple submissions, and we're still waiting for some more questions. But yeah, thank you, Tom, so much for your presentation. Really amazing examples and demonstration using MIDAS Civil. Yeah, and also I want to remind all the audience that you can submit your question by typing in the question box. And before we get into the Q&A session, I want to give you some time to submit the question. And before we get to the question, I want to introduce to all of you to MIDAS Expert Network. So if I can share my screen right now. Are you guys able to see my screen?
Looks like you're good to me.
All right. So yeah, so this is MIDAS Expert Network, and Tom, for example, is one of our experts in the network. All of the MIDAS experts are professional engineers across North America. We want to benefit users and, of course, forge a user community by having MIDAS experts engage with all of you. And here's how you can utilize MIDAS Expert Network other than attending the webinar. So, whenever you feel lost or stuck on your project and would rather speak with a peer user or engineer rather than going straight to our technical support, you can come to us and have us connect you with our MIDAS expert. And then we would connect a MIDAS expert who has specialty and extensive experience in the type of analysis and problem that you run into. And eventually we work out a time for about 15 or 30 minutes web meeting for you to share your problem and for the MIDAS expert to answer your question and share their experience regarding your dilemma. So again, this will not cost you anything. We're doing this because we want to, just like webinar, we want to connect more with our users, and we also want you to connect more with each other. So yeah, and then you can find our information on this web page shown on the screen. So I see a bunch of questions already submitted. So the first question is MIDAS able to calculate permit ratings based on a rating equation that has the demands from the secondary vehicle subtracted from the numerator?
So I think you're talking about if there's more than one vehicle applied, and in MIDAS there is a function to have a adjacent vehicle. So in your rating menu, you can actually tell it a primary vehicle and an adjacent vehicle. It's probably a two-step process for what you're looking at. So you might have to calculate it using both vehicles and then calculate it using only the single vehicle. And then if you compare the difference of the two, I think that would get you what your secondary number that you're looking for is. I hope that answers. It just might be a two-step process there.
All right, thank you, Tom. And then one last question since we're running out of time. So this user says, I usually perform load rating calculations outside of MIDAS Civil, and he would like to get your insight on the benefit of doing this in MIDAS versus outside of it.
I mean, there's a lot of benefits of doing it in MIDAS. Again, like I said, if you're doing design in MIDAS, then it makes your life really easy. You're not doing it going out to separate software. You're doing it all in one software, which is useful as a designer that I don't have to go create another model. I will say some of the limitations here or things that you have to watch out for is really just getting with your controlling agency. So a lot of the DOTs use, say, like AASHTOware as their primary load rating, kind of not just rating software, but actual bridge management software. And that may be linked up to their bridge network so that when they want to run a permit vehicle through, they've got a set number and they can pull the files of each of the bridges it might be going over and run that all through AASHTOware. So one of those limitations here is if you're doing the rating in MIDAS, you may still have to go out to, if there's any type of mandated software that's being used for that type of thing. Now, there's limitations within AASHTOware as well as what that can handle, and that still could kick you over into needing to use MIDAS anyway. But that's just one of those things where you might have to get with your agency to make sure that you're providing the information in a format that they can use and is best used within their management system. And again, the benefit here to me from the rating side is well, we're capturing the full 3D. We can do the rating equations directly in it for concrete, steel, and composite all within the same model. And if you're doing the design and then doing the rating with the design, there's no downtime or extra model being created. So I think those are the main benefits. Limitations being some of the stuff of just how it talks to other systems, or if there's a state mandated approach, be it Lars or AASHTOware or whatever other software they're using.
All right. I see there are actually a couple more questions, but we're running out of time since it's 4 p.m. already. So don't worry if you have asked questions and haven't answered a question yet. We will take a look at these questions and we'll get back to you. Also, we also have a discussion session for users who have specific questions for Tom right after this discussion. If you have not signed up for the session and have specific questions that you that you can think of after this webinar session, please let us know. We will have them answered. But other than that, I think this is it. And Tom, do you have any comments, or do you want to have something else to say?
No, I think I'm good. Generally, thank you all for attending. I believe the next the follow-up session is going to be under a separate meeting. Is that correct? So we'll jump out of this one and then jump into the other meeting.
That's correct.
Okay, so yeah, that's fine. But thank you, everyone. If you have questions, do send them on. I'm happy to answer via email or through the MIDAS network. We can do follow-up, one-on-one through the network as well. So just
all right,
let me know.
thank you, Tom.
Thanks.
Yeah, and thanks for everyone to attend. I really appreciate it.